Hi there, this is the video for section 2.3 on the topic of symmetric, complex, and Hermitian matrices. So in this section, we are going to really just describe and define some new types of matrices and see how to work with those things a little bit. Mostly this is going to be learning a little bit of vocab, some terminology, and just a few new mathematical objects. So let's start with the definition here. The transpose of a matrix is what we want to define first. So we say the transpose of a matrix A, excuse my document here, it's kind of dark there, not easy to read. The transpose of matrix A, if A is an M by N matrix, is going to be an N by M matrix. Notice I switched the dimensions there, and it's going to be denoted A with this little T superscript here, just as a label saying this is the transpose of A. And the way we define A superscript T, this A transpose, is by this definition. We can say that the ijth element, so the element in the ith row, jth column of the transpose of A, is the same as the element of A that's in the jth row and ith column. Right, so it's like we have just interchanged the row and column position to get the transpose matrix of A. Another way to state this is if you say C is, the matrix C is your transpose of A, then the ijth element of C is really the jith element of A. Right, again, we're just saying that the transpose interchanges rows and columns. And that's exactly what I've got here in plain language, that when you take a transpose, the first row of A becomes the first column of A transpose. The second row of A becomes the first column of A transpose, and so on. We do that for all the rows of A. So just to make sure we're on board with really how simple this idea of a transpose is, let's go ahead and find some transpose matrices in this example here. So to start out, in matrix A here, let's see what we get. Well, if this is our matrix A here, then the transpose, oops, I'm in a strange color here, let's switch to a standard black ink. The transpose of A, notice this is 2 by 2, that's like our M by N. And we said the transpose just has those reversed, but since they're the same dimension in both column and row, we get the same dimension here, also a 2 by 2 matrix. And all we're going to do to write down the transpose is take the first row of A, 3, 4, and write that as the first column of A transpose, 3, 4. Move on to your next row, negative 1, 6, negative 1, 6. It's just that easy. There's really nothing more to it. Let's see maybe something that could throw us off a little, just since it looks like a row matrix. This matrix B has a transpose. Let's see what it would look like. Well, matrix B itself has dimension 1 by 4 because it's 1 row and 4 columns. That means the transpose will be 4 by 1, right? So 4 rows and 1 column. And all we're going to do is take the row that makes up B and write it as a column to get B transpose. There you go. Simple as that. Let's move on to the last one here. Maybe you pause briefly and try this one on your own. I don't think it's any big challenge. But go ahead and write down C transpose, pause the video and try that if you'd like. I'm going to go ahead and write it down now. C is a 2 by 3 matrix, so we know C transpose is going to be a 3 by 2. Just swapping those out. And what do we get? First row of C becomes the first column of C transpose. Second row of C makes the second column of C transpose. So I hope we're convinced that writing down a transpose really isn't that tough of an exercise. So long as we see this basic way that it works, it will always work this way. Okay, let's look at some properties of these transposes. I'll even prove one that I think is pretty interesting. So some properties here, if you take a sum of 2 matrices, A plus B, and you take the transpose of that sum, it turns out you can actually take the transpose of each matrix individually before adding them. So A plus B transpose is A transpose plus B transpose. Similar, or also a nice simplification, if you have a scalar C times a matrix A, and you want the transpose of that scalar multiple, turns out you can just apply the transpose to A, and that scalar is not going to change at all. So you can take the scalar multiple first, then transpose, or you can transpose first, then multiply in the scalar. Doesn't matter. Either way works. Property 3 here says one that's pretty interesting that I want to try to do a quick proof of here below. It says the product A times B, if that's a well-defined product, if A and B have the right dimensions so that you can multiply those, then it turns out if you wanted to take the transpose of that product, you could take the product of the transposes in reverse order. It's kind of tricky because you have to remember that it has to be in the reverse order, but that's exactly what we're seeing here. AB, quantity transpose, is, even though A came first in the, on the left side, then B, on the right side, it's B first transpose, then A transpose. So it's kind of like the transpose applies, but also reverses the order of multiplication. And I'm going to show quickly, just with some formal notation here, how we can prove that statement. The last of these properties might be pretty obvious why it works. A transpose transpose, so the transpose of the transpose, gives you A back, right? All the first transpose does inside of here is interchanges the rows and columns. You do it again, you just switch them back, right? Switch the rows back to what were originally the rows. Okay, so let's see a quick proof of this one though. It's a little strange, so I like to prove it so you really, it gets a little more ingrained that it's an important one, maybe a counterintuitive one to pay attention to. And I won't expect that you can easily just out of nowhere sit down and write a proof like this with this notation I'm going to use, but hopefully seeing a proof really ingrains the idea that this is an important property that you want to be sure you're always clear about, remembering that switch of the order there. So let's try to prove this. What I'm really going to need to use in order to prove this is a fact that we've seen before, and it is this right here. This nice way that we can write out a matrix product. So before we even talk about proving property 3 here, let's just remember this. If we had A times B, two matrices multiplied together, the ijth element of that result, so the result in the element in the ith row and j column of the result of this multiplication, that's a matrix when we multiply these two out, what sits in the ith row and jth column is really representable this way. It's a sum from k equals 1 to r here. I should specify I'm thinking of A as being m by r and B as being r by n, so that this multiplication works out. Okay, so I'm summing over index r here, or from 1 to r, so I hit all of the columns of A and rows of B. Anyway, so assuming that I got my dimensions right here, A times B can be written this way, so that its ijth element is really just the sum over these inner indices. The k value is what I'm summing over, where I've fixed that the A entry is always looking in the ith row and the B entry is always looking in the j row. Right? That's how we multiply two matrices A and B. If this is A and this is B, oops, and this is B, then the result, A times B, if I was looking in the ith row in the jth column, the entry that sits there really says look at the ith row of A and take a dot product, just like a dot product, except assume these aren't incompatible, one's a row and one's a column. Take a dot product with the jth column of B. So when you kind of dot this row with this column, really a dot product is between compatible objects, not rows and columns, but here we're going to just say it's totally acceptable to do that. But anyway, if you remember how to multiply these matrices, you remember that what sits in the ith row and jth column of the product really came from looking at the ith row of A and the jth column of B. So that's all I'm describing right here, is that element that sits right there is what you get from taking the ith row of A. I've got the I always indicated in the row index on A, and the j column of B. So I've got the j always indicated on the column index of B. And all we're doing is multiplying this entry here times this entry here. That's like k equals 1, the first entry here and the first entry here. Then the next entry with the next entry. That's like the k equals 2 term in this sum. All the way up until the last one. That's like the R entry. That's the R column here, the R column here. So you go from k equals 1 to R. Go through all of these combinations. And so when you're multiplying each of these pairwise like this and adding them up, that gives us this nice way of writing it with this summation notation I've gotten here. So what can we do? If we remember that this is a nice way to write this product, it's not so bad. Up here, all we're going to do is write an expression for the ijth element of the transpose of AB. But the immediate thing I'm going to do is I'm going to say this is the same as the jith element of just AB. Right, if I didn't take the transpose, it would mean all my rows and columns would be switched. So if I wanted to look at the ith row jth column of the transpose, that's the same as looking at the jth row I column of the not transpose product. So what can I do from here? I've immediately gotten rid of the weird part, that transpose. What can I do now? Well, I know how to write a product of two matrices. I know how to write a specific element of it with this sort of notation down here. Notice I'm looking at the j row I column. Here is the ith row in j column. So I'm going to switch the I and the j here and here and just write what I get. You take the jk element of A and the bki element of the ki element of B. Right, I'm just switching the I and j in this formula because they're switched in the expression I'm working with. And so what do we get from here? Well, the nice idea from here is that, check out what we can do. Remember, we're trying to say that the original transpose of the product is somehow related to the product of the individual transposes. So I need to incorporate those transposes back. How do I do this? Pretty easily, actually. I can rewrite this in terms of A transpose. If I wanted to look at the j row k column of A, that's the same as the k row j column of the transpose. All the transpose is doing is switching the row and column index. Same with the B matrix. I'll write this as IK. And now maybe this is the big leap. Remember, each of these terms written in this summation are just a scalar times a scalar. ATKJ right here, that's a transpose KJ. That's just a scalar quantity that sits in the k row jth column of A transpose. BTIK, that's just a scalar quantity sitting in the ith row k column of B transpose. My point is, since these are scalars, you can commute these. This scalar times the one to the right is the same if you reverse the order. You can't reverse the order of multiplication in two matrices, but you can reverse the order of multiplication between two scalars, which is all we have here. So what do I have? And I'm hoping this looks super familiar. Look again back here now. I've got almost exactly what's sitting here, written over here, except I'm using B transpose instead of A and A transpose instead of B. So I know this is just the ijth element of B transpose A transpose. Right? So what have we shown? We've shown the ijth element of AB transpose. is the same as the ijth element of B transpose times A transpose. Since the ijth element is the same regardless of which row I and which column J we're talking about, it means AB transpose is equal to B transpose A transpose. These matrices who have all equal entries must be the same matrix. And that proves our result. And so I think this is a good proof to get you thinking about how you can use this sort of notation, this summation notation in proofs. But like I said, I wouldn't expect you to reproduce or come up with a proof like this just out of nowhere on your own. And really my point in showing you this is that hopefully it will stick with you now that AB transpose is not A transpose B transpose. It's B transpose A transpose. The order is so specific, I think it's worth the whole proof just showing how we reverse that order. That step came here, dealing with these scalars. Hopefully after seeing that, this one will really stick with you. Okay, enough of that proof, let's go on. I do want to mention some other use of transpose that tends to be pretty common, pretty useful. Notice that if we have column vectors V with components V1 through Vn and U with components U1 through Un, if we write, got my vector hats here, but if we write U transpose V, what is that really? The U, it was a column, but now it turns into a row because we took the transpose. This is U transpose times V. And the V we'll just think of still as a column matrix here. And now notice what happens when we multiply 1 by n, that's how big this U vector was, this U row vector. N by 1 is how big the V vector was. The inner dimensions do match, so we can multiply. And when we do, the result should be 1 by 1. And look what happens if we actually do this. When you do this sort of process, you're actually just laying this V vector over the U vector, multiplying component-wise and adding the results. Essentially, I mean, not essentially, exactly, we're taking a dot product. So in a very formal matrix multiplication sort of way, U transpose V, where U and V are both column matrices, is the same, produces the same result, is just dotting your two vectors. You might say, well, if I'm dealing with matrices, then when I dot them, or when I multiply them this way, one matrix transpose times another, I'll still have a matrix at the end of the day. And that's true, you will have a matrix, but it's going to be 1 by 1, right? It's a matrix with a single number sitting inside of it. And it turns out that with the rules of matrix arithmetic and algebra, there's no difference between a 1 by 1 matrix and a scalar. So it is completely safe to say that U dot V is in every way that we care about exactly the same as U transpose V. Right? Dotting these two vectors gives you the same result as taking U transpose V. One reason you might do that is if you want to be very consistent with your matrix operations here. A matrix multiplication is defined in a very specific way. This is maybe going to let us mix this with multiplication on other matrices more easily than a dot product would. Okay. So a couple little notes here. Since we have in the past seen that you can write the norm of a vector as the square root of its dot product with itself. Here we're just saying, well, since the dot product of two vectors is the same as first one transpose times the second one, you're thinking of columns here, this is a very common way to write the norm of a column vector, right? It is the square root of U transpose U. It just follows directly. Similarly, we could say that two columns are orthogonal if and only if U transpose V equals 0. Right? It's just like saying a dot product is 0. We've seen that in a previous video. Okay. And it should be mentioned, there's nothing special about columns here. They're useful in many cases, but you could just as well express U and V as row vectors. And then in order to express the dot product, it would actually be U V transpose instead of U transpose V. Switching these to rows, first of all, will mean that you need to switch which one gets the transpose. And you can work that out and see it works essentially the same way we described up here. So let's look at a definition here. Finally, get into some stuff we're going to kind of use pretty frequently here. A symmetric matrix A is a square matrix that's equal to its transpose. So if you're wondering why are we defining this thing where you just switch rows and columns, one reason is that we want to define a symmetric matrix because these we'll see have very special qualities. A symmetric matrix is just a square matrix that's the same as its transpose. Performing the transpose changes nothing. In other words, the ij element of A is always the same as the aji element, right? What's in the ith row and jth column is the same as what's in the j row and ith column. This notation might be a little strange until you've gotten used to it, but I think we'll start to see what this is really describing. So I've written down a couple of symmetric matrices here, 2, 1, 1, 3. Notice if I took the transpose, of this, what do I get? First row becomes first column, 2, 1. First row becomes first column, 1, 3. But this is exactly what I started with, right? 2, 1, 1, 3 transpose is 2, 1, 1, 3. So this is symmetric. The same thing goes for this matrix here. This is also a symmetric matrix. And once we see a bigger version of it like this one, maybe we're starting to see visually what a symmetric matrix looks like. It looks symmetric across that main diagonal here, right? What's on the main diagonal doesn't really matter. You can have anything on the main diagonal. But what's on equal and opposite sides of that main diagonal must be equal. So if you go, I don't know, from any element on the main diagonal, say this one, if you go up 1 or to the left 1, you should get the same element. If you go to the right 1 and up 1, you should get the same element as if you go down 1 and to the left 1. Let's see why that is. Let's give this matrix a name. Let's call it A. In this case, A2, 3, for example, what does that equal? Second row, third column, second row, third column. It's this guy. Well, I'm claiming this is symmetric. I'm claiming that A3, 2 must be the same thing, meaning third column, second row. Sorry, third row, second column. Third row, second column. Third row, second column, that's here. Yep, that's also 3. And you can check this for every element, for every index, for every row and column index from 1 to 3. Write any of these down and they'll all be equal, right? I mean, write down the aij and then the a, eraser's not working with me here. The aij and the aji element, and they'll be the same for any values of I and j between 1 and n. In this case, n equals 3. So as a little exercise here, let's go ahead and take this matrix that I've set up to be a 5 by 5, and let's fill out the other half of this matrix so that it becomes a symmetric matrix. Right, so you might want to do this, pause the video and see if you can do this real quick. I'm going to go ahead and fill it in. When I do this right here, I should have, this is the second row, first column. So I need to look at the first row, second column to see what it needs to match. It's this guy. Third row, first column, that's this element. So I should look at the third row, sorry, first row, third column. First row, third column, this guy. Okay. And maybe you're just seeing it as a pattern of making it symmetric across that main diagonal. I think that's a great way to do this. Get a 3 here, 4 here, 6 here, -1, -5, 1, and it looks like -4, 3. I did that in sort of a scattered way, but I got there. I got to my final answer. Okay, so those are symmetric matrices. We do need to define just very briefly something we won't use often, but we need to get the basic idea down. This definition here defines what we call the trace of a matrix, of a square matrix. And if we let A be a square matrix, the trace of A, denoted TR of A, just like I've written here, is the sum of its main diagonal elements. So you're hopefully seeing right away, this is almost trivial to compute, right? If you take a matrix that's square, you're just looking down the main diagonal and adding all those elements. Like I said, we won't use this often, but it is useful to know this term, know what the trace really is. I like to include this summation notation for these things whenever I can. This is saying add AKK for all values of K between 1 and N. So that's A11, A22, all the way up to ANN. You might identify this already, that when your indices are the same, that's an element that sits on the main diagonal here. So we're just saying add all of those. First row, first column, that'd be the 2 up here. Second row, second column, that'd be the 6 here. Third row, third column, fourth row, fourth column, and so on, all the way to the end of your matrix. Well, since you're adding all those up, you can certainly use summation notation to represent this more compactly. Quick properties of the trace. Like I said, we're not going to see much of trace in our class. So let's just briefly gloss over these. The trace of the sum is the sum of 2 traces. That's nice. The trace of AB is the same as the trace of BA. So while matrix multiplication doesn't commute, the trace of a matrix multiplication doesn't care which order you multiply in. That's nice. 3 here. The trace of a scalar multiple of A is really the scalar multiple of the trace of A. So instead of taking C times A, just take the scalar C outside the trace, compute the trace of A, multiply the C in at the end. Finally, pretty nice one here. The trace of A transpose is the trace of A. This should follow immediately from what we have up here for our definition. If we're looking at A transpose or A, right, the elements along the main diagonal are the only ones we're adding. So it's the 2, 6, 7, 4, 2, and 4 here. If we took the transpose, since they're on the main diagonal, everything else is just flipping around that. So you wouldn't even see these guys move. So certainly if you added them up for the transpose or A themselves, or A itself, you'd get the same trace. Okay, just a little more here. I do want to mention complex matrices here. It's important that we identify that we can have these matrices that we typically see containing real numbers as their entries. There's no reason they have to have real numbers as their entries. You could have complex values. So you could actually have different things than that even, but complex is maybe the other most useful one other than real values. So I want to just recap very briefly what we've already seen about complex arithmetic and algebra. If we have matrices with complex valued entries, we must remember, given these complex numbers as their entries, the key thing to remember about complex is that I, when we see it, represents the square root of -1. Maybe more importantly, that means when we square I, we get -1. So I've written down here a brief reminder of how the operations work on on complex numbers with real parts A and B or C and D. So this might be worth recapping if you don't remember or want a little refresher on complex stuff. We've already seen a little bit of that in a previous video. So I'm going to jump past that a little bit. It turns out all the usual rules for matrix arithmetic still apply if the matrix has complex entries. It's just you have to be careful with how you add or subtract complex numbers, or multiply them in the case of doing a matrix multiplication with complex entries. Now, once we've established the idea that there's no reason we should exclude complex numbers from being our entries of our matrices, then we can define a few more objects, a few more types of matrices involving complex stuff. So here's a definition getting right to that. The conjugate of a matrix A is denoted A bar, just like the conjugate of a complex number was, Z bar. And it's defined by the fact that the ijth element of the complex conjugate of A is really just the complex conjugate of the ijth element of A. All you're doing is going through the entire matrix and taking a conjugate of every entry. That's all we're doing. Take a conjugate of every entry of A to get A bar, the conjugate matrix of A. Now, if you take the conjugate and then you take a transpose, we call that the conjugate transpose of A, and it's denoted A with a little star up here in the superscript. Really, you could write that as the transpose of the conjugate, or you could write that just as this notation altogether, bar T, like this, A with a bar, then a T. But we will typically use that star to represent conjugate transpose. And really, the conjugate transpose really plays a useful role for complex matrices the same way that the transpose will for real matrices. So just like we defined a symmetric matrix, it's useful to a symmetric matrix that really had to do with that transpose for real matrices. It's also useful to define what we call a Hermitian matrix, very similarly with the conjugate transpose for complex matrices. So here we have it, a square matrix A is called Hermitian if A is equal to its own conjugate transpose. This really is like, it's not the same, but it's similar and useful in similar ways to how these symmetric matrices, except for complex matrices. Now, I'm not saying you can't, I'm not saying you can't apply these ideas to real matrices. I'm just saying that the real reason we do it is because Hermitian becomes nice in the same way that symmetric is for real matrices, except for complex ones. Hermitian is useful there. So a couple little examples here, kind of giving a few of them away at the bottom of my screen here. Let's see. If I have a matrix A equals 2 minus I, 3 plus I, 1/2, and I, what does the complex conjugate transpose look like? Well, first you want to take, ooh, I didn't even do this, did I? No, I didn't. This is wrong what I had written here. If A is this matrix, and I want the conjugate transpose, I would first take a conjugate. So I switch all the signs on every imaginary part. Real parts don't get affected. So that half just stays as a half, but all the i's get switched to negative i's. Now, in order to take A star, the conjugate transpose, now we would take the transpose of that result we just had. That would be A star. Yeah, big mistake here. This is bad. But notice when we take the conjugate transpose of matrix A, what are we left with? Let's even remember what A was. A was this matrix way over here. Notice this does not equal A. This is a very different matrix than A. So we know A is not Hermitian. Okay. And so down here, in fact, let me do this a little differently. I'm moving away from my screen. Seeing if I can hide a couple things from you. Maybe you already saw the punchline here. That's okay. What do we have? So my notes kind of gave away the answer to this one. But the idea for this was I give you part of a matrix and I want you to fill in the blanks to make this Hermitian. Right? So what does that mean? If this is like our matrix A, what would the conjugate transpose look like? Well, right, that's the conjugate, just with the transpose applied. The conjugate itself, before we even apply the transpose, the conjugate's pretty easy to write down. Right, just flip the signs on all the on all the imaginary parts. And I don't actually have entries for the rest of them. So let me just write like Z1, Z2, Z3, Z4 here. Now, when I take the conjugate, that means those are all conjugate. Z1 bar, Z2 bar, Z3 bar, Z4 bar. So there we go, we did that. And now look what happens. If we go ahead and apply the transpose now, now we've fully got conjugate transpose. Just gonna have to finish writing it down. Oops. I made a mistake there. And finally, this is what we have. Right, so we're saying in order to be Hermitian, the conjugate transpose, which I've written out here, has to equal what we started with, has to equal A. And you might be saying, well, now I have to somehow figure out from here, okay, if Z1 conjugate is a 3, then what is Z1? It's actually not that hard because think about it from the other direction. If you have Z1 here, that must be the 3 that you have in the corresponding entry over here. If you have a Z2 right below that, Z2 must be negative I. If you have Z3 right here, that must be the I in the corresponding spot to the left of the equation. Z3 and Z4. Ooh, what's happening here? Right, I didn't give you that one main diagonal element. And we're saying Z4 has to equal its own conjugate transpose, or its own conjugate. So what is our requirement here? We've figured out Z1, Z2, and Z3. Let's go ahead and fill them in. Z1 was 3. Z2 is negative I. Z3 is I. You might be able to see those patterns there. You're just taking a symmetric matrix, but making sure any complex stuff gets a conjugate on opposite sides of the main diagonal. Except for this one. This one's complicated, right? Z4 equals Z4 bar. Well, let's figure out what that means. If Z4 is some complex number, A plus IB, the fact that it equals Z bar, its own conjugate, means it equals A times A minus IB. Right? For these two to be equal, what has to happen? Well, you could subtract A from both sides. You could add IB to both sides, and you get 2IB equals 0. Well, the only option here, if you have 2 times I times B to equal 0, 2 isn't 0, I isn't 0, that means the B must actually equal 0. So all we're saying is the form of this Z4 has to be this so that the imaginary part is 0. It has to be a purely real number. But so long as it's real, we're good. So long as it has 0 imaginary part, we're good. So let's plug in anything we want here. Easiest real number, 0. I'll put that there. Oh, and I forgot my Z2. Okay. So there you go. We filled in the blanks to make this a Hermitian matrix. See if that's the same answer I already gave away in my notes. 3, negative I, and something with the imaginary part equal to 0. That is it. That does it. Some brief properties about these conjugate transposes. If you have the conjugate transpose of a sum, that's the same as the sum of the 2 individual conjugate transposes. It's kind of like it distributes. The conjugate transpose of a product works the same as the transpose, right? It reverses the order, but can be applied individually to the matrices. If you have a complex scalar, So a non-matrix quantity Z that's complex, and you multiply that on matrix A, and you want the complex conjugate of that scalar multiple. It turns out you need to take the conjugate of Z and the complex conjugate of A. That's all you have to do. You can break it up into individual parts like that. And again, just like we saw with the transpose, if you apply the complex conjugate transpose twice, that just undoes its own effect and gives you back A again. Right? This is applying this twice undoes its own, undoes the effect of applying it in the first place. Okay, you might be able to see why that is, right? If you switched all the rows and columns and flipped all the signs on the imaginary parts, that's one conjugate transpose applied. If you do that again, you're switching all the rows and columns back to their original positions, and you're switching all the signs on the imaginary parts once again, so it puts them back to their original signs. You're switching all the rows and columns once and then again, and you're switching all these signs on the imaginary parts once and then again. So applying that twice does nothing at all to A. Okay, that is it for this video. In the next section, we're going to go a little bit further talking about these matrices. We'll see why we like that transpose. Sorry, just one second. Let's see. Sorry about that. I had a technical difficulty on my end here. In the next section, we're going to look at these matrices a little bit more and make a connection back to systems of equations. Really, we want to see how to use the matrix inverse to help us solve systems. But that's it for this video. I will see you in the next one. Thanks for your attention.